Okay, so the last thing that I want to talk about today is power in waves. So as I mentioned a few times, waves themselves, the disturbances in the medium, move along in one direction. And because they're disturbances, because they carry with them some amount of energy, we can think of that energy as being transported. And the natural way to talk about energy being transported is in the language of power. So if I kind of draw this out schematically, think of a wave pulse. So I start off, my wave pulse is here, and it's moving to the right. If I think of t equals 0 as maybe something like this, then all of the energy is over here, and there's no energy on the right. If I look at it after a little bit of time, that wave has moved along. Now all of my energy is on the right-hand side of this cut, and none is on the left. So if you think about it, the amount of energy that passes across this cut per unit time is a power. Power is telling me how much energy passes across any point as a function of divided by time. And so that's for a single wave pulse. For an entire traveling wave, it's continuously transmitting energy or power across any point along the wave. So it turns out the waves are going to move energy. And if you think of them as kind of a collection of harmonic oscillators, it's pretty clear they're actually transporting both potential energy, think of that like the spring energy of that string, and kinetic energy. Now, it's not that complicated to derive the amount of power transmitted by the wave. I'll do that after class or in the lecture notes if you're interested. But I'm not going to do that right now. It's just a little bit of calculus. The thing that you do need to know is that for waves on a string, there are actually two different formulas. So the actual amount of power at a given position and a given time is time dependent. The formula, which I will derive after class, is 1/2 square root mu f omega squared a squared times sine squared of omega t minus k times x. Okay? So there's this overall prefactor. I'm sorry, there's no 1/2 right there. I should say that. So there's this overall prefactor, square root mu f omega squared a squared. That's the big one. That's what's doing the majority of the work. The sine squared right here simply tells you that there's some time dependence there. And what happens is when the wave is maximal, so that's cosine of omega t minus kx is maximal, that means sine squared is 0. At those particular points in time, it actually isn't transmitting any power. So if I look at my wave function, if I'm sitting right here, the power actually at that point is 0. If I'm sitting right at the 0 point of the wave, the power is maximal. In that case, I can just use this formula to figure out that the power is, one second. There we go. Square root of mu f times omega squared times a squared. And in between, it goes between these two values. So there are two quantities that we want to characterize: the average power and the maximum power. So the maximum power is what we just talked about. It's right there where the wave function goes through 0. And that's maximum power is equal to square root of mu times f times omega squared a squared. The average power is not that complicated. So if you look at the sine squared function, the sine squared function oscillates between 0 and 1. So the average of that is 1/2. And that means that the average power is 1/2 square root of mu times f times omega squared times a squared. So the average power is actually the thing that we're most often going to talk about. The reason for that is, let's say I'm talking. So right now I'm generating sound waves. Omega is so fast that if you were to actually put a little, let's say, a sound meter to detect how much power is coming out of my mouth, you wouldn't see the very, very, very fast wiggles at the frequency omega or the period t. You just see the average. And the average is usually the more important quantity. But indeed, we can characterize it both by the average, the maximum, or indeed this whole time-dependent expression. So the big takeaways are waves transmit energy or power. The average power, this is the big formula we will use, is 1/2 root mu f omega squared a squared for waves on a string. And the average power, you'll notice, is proportional to the square of the frequency and the square of the amplitude. So for those of you who do continue with me, let's say to 2326 or even further on, you'll see this is actually a very general property of wave physics. It's proportional to the square of the frequency, square of the amplitude. So there are various reasons you can think of that as kind of the velocity of the string, right? A times omega is like the maximum velocity, and energy is like velocity squared. So that's omega squared A squared. But it's actually a general rule, and we'll see it again if you come to electromagnetism. At any rate, that's how waves behave on a string. Now there's one other way that we can think about waves, which is spherical waves. So you can imagine, for example, the sun. The sun is a generator of electromagnetic waves. We'll learn about those in 2326. You can think of my voice as a generator of sound waves. You can think of any particular point-like object as generating waves. So when that happens, those waves are going to propagate in every direction. So for example, at the surface of the sun, you generate light, which is a form of wave, and it just goes off in every single direction. So if here's the sun, the Earth might be over here, but Mars is also getting light from the sun. Jupiter's also getting light from the sun. It's going off in all directions. And so the relevant piece of physics here is not what is the power, because the power is ill-defined. The power at a given point, let's say this is the Earth. The power at the Earth is somewhat ill-defined. What matters is how much of that light reaches the Earth as opposed to just goes off into deep space. So in order to understand that quantity, we're going to define something called the intensity. The intensity is defined as power, average power, divided by 4 pi r squared. So imagine I have a point source, an object that is very, very small. We're not going to consider its dimensions like the sun. And we want to know how its energy falls off with distance. So first off, the sun itself is a source of radiation. It is producing energy at a constant power. So if here's my sun, it shoots off light in all directions at a constant power, or an average power, which let's just say is some number. So we don't have a formula for that. It'll be related to that formula I told on the previous slide, but we don't need to worry about that. And the question is, if I'm sitting at radius r away from the sun, how much of that energy hits me? Okay, so let's consider some amount of time delta t. The amount of energy the sun produced is just power times time. So power is energy over time. That means the energy of the sun is power times time. Okay. And now let's figure out how that is distributed at radius r. So at radius r, energy is conserved, assuming no waves are emitted or absorbed along the way. So energy is conserved, meaning all of that energy ends up at radius r. And what's the surface that is sitting at radius r from the center of the sun? What is that surface called? It's called a sphere. Meaning that energy, E sun, is evenly distributed over a sphere. Of radius r. So now we see that there's a relevant quantity here, which is the energy divided by the area. That's just the energy of the sun divided by the area. 4 pi r squared. That's the surface area of a sphere. Or in other words, the power that hits the Earth per unit area, so for example, this would be like the cross-sectional area of the Earth, is equal to the power produced at the sun divided by 4 pi r squared. So this is a very important quantity. It goes by the name intensity, and we label it by I. So the intensity of waves is defined as the average power over 4 pi r squared, where r is the distance from the source. And the important thing is that intensity, so power is given to us, that's basically set by how strong the source is. The intensity depends on radius. So you see that intensity is proportional to 1 over r squared. If I rearrange this a little bit, I can talk about two different radii. So let's say here's the Earth. Earth is at radius r1. And then way out here is Jupiter maybe at radius r2. Here's the center of the sun. What's the relationship between the intensity of light at Jupiter and at the Earth? So what we can do is we can solve for power. Let's go back to this equation. So the intensity at radius r1 is power, which is just given to us by the sun, over 4 pi r1 squared. Or in other words, if I solve for the power is 4 pi intensity times r1 squared. I can do the same thing for Jupiter. I2 is p over 4 pi r2 squared. Solve for power. I see that this same power is 4 pi I2 times R2 squared. So these are both equations for the power. If I solve them together, set them equal to each other, the 4 pi's cancel. I rearrange and I find that I1 over I2 is R2 squared over R1 squared. This is called the inverse square law. That's the way that it decays is 1 over R squared. And so that's going to be something that you see a lot as you continue in physics. The way that radiation decays on a sphere is 1 over r squared, and that just comes from the fact that the area of a sphere is proportional to r squared. All right, so this is the relationship between the intensity at two distances. That would be power if you have a center, a single source of light that's propagating in all three dimensions. If you have a wave on a string, here is the average power that you want to use. So let's go ahead and get just a little practice on this. So the sun, as I've mentioned, is a powerful source of waves. The radius of the Earth is this, the radius of the sun is this, and the Earth-Sun distance is 149.6 million kilometers. So go ahead and use our formula, figure out what is the intensity of radiation on the surface of the sun, what is the total power output of the sun, and then let's go ahead and compare that to the world's largest power station. Okay, very good. So here, we're given a little bit of info. We're given the sun right here. So we're imagining it as a point source of radiation, spewing out radiation at some average power, which we don't know. That's going to be part B. However, we do know that at the Earth, which is much, much further away than the surface of the sun, so here's my Earth, at that radius, which I will call our Earth, the intensity is 1.368 kilowatts, meaning times 10 to the third watts per meter squared. The units of intensity are watts power divided by area, meters squared. Okay. And we know that the radius of the Earth, the Earth-Sun distance, this is the distance between the Sun and the Earth, is 1496 million kilometers. So if I write that out, it's 1.496 times 10 to the 6 plus 2 is 8 kilometers. Or if I convert that into meters, 1.496 times 10 to the 11 meters. Notice I don't care about the radius of the Earth itself. I care about the distance between my point source of light, which is the sun, and the Earth. So that's RE here. And finally, we're given that the radius of the sun itself, RS, is 696,000 kilometers, or 6.96 times 10 to the 8 meters. And we're asked to figure out the intensity of radiation on the surface of the sun. So here we're going to go ahead and use that inverse squares law, which tells us that intensity is equal to power over 4 pi r squared. Or in other words, intensity of the Earth over intensity at the surface of the sun is equal to radius of the sun squared divided by the distance to the Earth, RE squared. All right, so we have everything in this except for IS. Let's go ahead and solve for it. So I'll multiply both sides by IS, divide both sides by this expression right here, and I get that IS is equal to I Earth, R Earth squared divided by R sun squared. Plug in some numbers. The answer you should get is 6.32 times 10 to the 4. And the units are again, 10 to the 7. The units are again watts per meter squared. I have it written in the notes as 6.32 times 10 to the 4 kilowatts per meter squared, which is also fine. So I was a little more cavalier with units in the notes. They're correct, but let's just go ahead and stick to SI here. All right, good. So that's the intensity at the surface of the sun. Part B then asks, what is the power output of the sun? So this is perhaps the more useful formula, is that the intensity is equal to the average power divided by 4 pi r squared. And that's true for the sun or the Earth. So that's true for the distance at between the Earth and the sun. Or we can just do this using our thing that we just calculated for the at the surface of the sun. Let's go ahead and use the Earth. It doesn't really matter, but I like the Earth. So the average power, if I resolve this equation, is 4 pi r squared times intensity. And here I'm going to take the Earth-Sun distance, RE, as my radius, and I at the Earth as my intensity. So you go ahead and plug in some numbers. This turns out to be 3.85 times 10 to the 26th watts. Or, if you like megawatts, 3.85 times 10 to the 20th megawatts. All right? So that's about 1.7 times 10 to the 16th of the single most strongest power station on Earth. The upshot of this calculation, which should come as no surprise, is that the sun is a very, very powerful source of electromagnetic radiation. All right, so that's all I wanted to cover for now. For those who are not interested in a little bit of extra material, thank you for listening to this lecture. The important take-home messages here are that waves are disturbances in a background. A common example of a wave is, for example, shaking a string. So for the string, we derived the velocity, we figured out the relationship, this wave equation, and the wave function, y of xt is equal to a cosine kx minus omega t, which tells us everything we need to know about the wave. And finally, at the end, we saw that this could transmit power, either from a point source, from a traveling wave like this, or from a point source like the sun. For those who are interested, I'm going to do a couple of extra things here. First, I'm going to talk a little bit about how that wave equation was derived for the string. And then I'll go ahead and derive this relationship, the power transmitted by a wave on a string. All right, thanks. Bye.